Okay, so section 6.2, this covers this method of moments estimation. And so the context is we've got a random variable, and we know it's PDF. And that PDF depends on k different parameters, theta 1 up to theta k. So what we just saw in the previous video, the previous slide, is that when we calculate the theoretical moments by doing some integration or maybe some summations, those are going to be functions of the parameters theta 1 up to theta k. When we calculate the sample moments, we actually have values x1 up to x whatever, xn. So we take those values and we can calculate the sample moments. Those are going to be constants. And so the method of moments is going to be an estimate that we get when we solve a system of equations. So the method of moments is kind of like an algebraic method here. So what we were saying earlier is that we want to make sure that the mean of my sample matches the mean of the population. And so that we could summarize by saying we want the first theoretical moment to be equal to the first sample moment. And if we have more than one parameter, then we would need to continue on. So here, what we're ultimately trying to solve for is the values of these k parameters, theta 1 up to theta k. So if we need to solve for k unknowns, we would need to get a system of k different equations. So the second equation, if we have more than one parameter, would be what we get when we set the second theoretical moment equal to the second sample moment. And we continue on with all of these equations. We calculate the kth theoretical moment. We evaluate and calculate the kth sample moment. And so the result of all of that is a system of k equations in k unknowns. Again, the unknowns here are the thetas. So we need to set up and solve this big system of equations. And one thing I should mention here is we can do this whether the random variable is continuous or discrete. And so if you were dealing with a discrete random variable, instead of integrating, you would be summing over all of the possible values of the random variable x. So we get a system of k equations in k unknowns, and solving that system is going to give us the method of moments estimate for each of our parameters theta. So let's take a look at this in the next example. Okay, so we previously took a look at the random variable x that had this PDF function lambda e to the minus lambda x minus delta. So this involved two different parameters, delta and lambda. So the method of moments, therefore, if we're going to use this to estimate the values of lambda and delta, we're going to want to set up a system of two equations. Comparing the first and the second theoretical and sample moments. So a couple of slides ago, we found the first and second theoretical moment for this random variable x. And then we calculated the first and second sample moment. So I've got one equation by comparing the first moment by saying delta plus 1 over lambda needs to equal 5, which was the sample mean, the first sample moment. And then we have a second equation, which is the second theoretical moment, which we calculated previously to be delta plus 1 over lambda squared plus 1 over lambda squared. And that needs to equal the second sample moment, which was 28.5. So we've got this system of equations. I'll box it in. So we have two equations here with two unknowns. It's a nonlinear system, but we can still solve it. So find the method of moments estimates is going to require us to solve this system of equations for delta and lambda. So if I want to solve this system, one thing that we can do is notice this quantity right here is the same as this quantity right here. And so if I know that that is equal to 5, I can go ahead and substitute 5 in for delta plus 1 over lambda. And so when I do that, that would give me this 5 squared plus 1 over lambda squared, that needs to equal the 28.5. So now we can solve for lambda. For example, we could subtract the 25 from both sides, and then take the square root, and then take the reciprocal, and that's going to give me my estimate for lambda. So I'm going to put a hat on top of this, and I'm going to put a MOM to denote that this is the estimate obtained by the method of moments. And in this case, that would be 1 over the square root of 3.5, which I'll estimate to be 0.535. And then once I have this, I can go ahead and substitute this into the first equation that we had from comparing the two first moments. So in other words, I've got delta plus 1 over lambda, which we just approximated with 0.535. And I know that needs to equal the first sample moment, which was 5. And that gives me an estimate for lambda that I'll call lambda hat with a subscript of MOM for method of moments, which comes out to approximately, we're estimating this, 3.131. So that would be my estimate for delta, and over here we found our estimate for lambda. So that's how we came up with our estimates for the two parameters in this PDF function by comparing make sure that our population mean equals our sample mean, and then to make sure that our population variance essentially is equal to our sample variance. So that's what we're getting when we compare the first two moments. So in the next example, the next slide, we're going to take a look at another example where we're picking out of a uniform distribution. So we'll walk through another example from start to finish of how the method of moments would work.